Thank you very much. Good morning, everyone. So today I will be talking about tumor analysis applied to high-Z cosmological simulations, especially clumpy disk galaxies. And this talk is closely related to the last talk yesterday afternoon given by Neil Mandelker. But Neil has already shown my most important figure, so I may no longer need to give a talk today. But anyway, I talk about the formation of giant clumps in cosmological simulations. So this work was performed with some collaborators listed here. So my name is Shigeki Inoue from Hebrew University of Jerusalem. Okay, first of all, today I'll talk about this clumpy disk galaxy in high-Z universe. So this is the observation about redshift 1, 2, 3. So, and these clumpy structures, these clumpy galaxies are thought to evolve into local disk galaxies with smooth density distribution, but it may not be possible. But the clumpy structures has a mass of roughly 10 to the 9 or 8 solar mass at the largest. And a significant fraction of high-Z galaxies observed to be clumpy by these observations. So the clumpy galaxy is not rare galaxy, but typical galaxy. Okay, so then my topic is does tumor instability form clumps? So the tumor analysis tumor parameter can be defined like this. So sigma is a velocity dispersion and internal pressure. And kappa is a shear motion. And internal pressure and the shear works as a support of the gravity. So that sigma, this density, is represented by gravitational contraction. Okay. And if the Q is more than 1, the local region is supposed to be unstable and start collapse. So, and at low Z disk galaxies, these are typically gas poor and non-perturbed, less perturbed. They don't have so much minor mergers. So tumor instability are thought to result in formation of spiral arms. On the other hand, in high-Z galaxies are largely different from local low-Z galaxies. These are typically gas-rich and highly perturbed by, for example, minor mergers and pre-existing clumps, maybe triaxial halos, something like that. Anyway, the tumor instability has been discussed to result in the formation of giant clumps. But this proposition was done by very early works, the earliest works on this kind of galaxy. So what I want to do is that, I want to know this scenario is true or not. Okay, so I utilize cosmological simulation shown here, performed by Severino et al. Using an AMR called ART simulation. So this simulation has a very high resolution and radiation pressure has been implemented in the simulation. Okay, so this is showing how to compute tumor Q in my analysis. I compute Q for gas and stars separately. And I got 2Q, and the 2 Qs can be combined like this. So I can get 2-component Q. This is more accurate than 1-component analysis. So here, and a unique point of this method is I used local mean velocity to determine kappa. So usually in some studies, kappa is measured using circular velocity determined by potential gradient. But I use local velocity field to determine, turbulence and perturbed disk galaxies. So, and using mean velocity is usually leads to lower Q than using a circular velocity. So, and next I remove the Barrage stars by this criterion, and I applied Gaussian smoothing with roughly 1 kpc scale. So to smooth out small structures. So to focus on this clump size, clump mass. So I focus on massive clumps. So, and I use laser thin disk model Some studies apply thickness correction or something like that, but I assume razor thin disk for the high-Z galaxies in order to get lower limit of Q. So the concept of this method is that I want to get Q as low as possible. Okay. Everything. Surface density, velocity field, anyway, everything is applied. Okay, next one. This is the first example of the galaxy. I applied this analysis. So this is a very massive galaxy at radius about 2, and the gas fraction is about 25%. And the BOT ratio is here, and the star formation rate is roughly 30 mega year per year, 30 solar mass per year. So this is a gas surface density and the stellar surface density, edge zone and phase zone. So this galaxy has many clumps in the extended disk region. So, and I applied the Gaussian smoothing for these surface density, velocity dispersion, and the kappa, and I got Q distribution for gas and stars here. And I combine the two Q distribution, and finally I got the Q distribution as a two-component Q. So, okay, let me explain the color indication. So the purple color indicates Q smaller than 1, in which gravitational contraction happens in linear fashion. So linear instability is purple in these regions. And the blue region indicates a Q value lower than about 1.8. So this region is also unstable in nonlinear fashion, in which perturbation grows slowly. On the other hand, and green region indicates Q smaller than 3, about 3. This Q is supposed to be dissipative instability. If gas cooling is efficient, the green region may be unstable. But basically, so it's not standard to instability. Okay. And the red, yellow, and black are indicates Q larger than 3. So these region, for example, these region supposed to be stable in two-dimensional analysis. And the white region around here has imaginary kappa. So I use the actual velocity to determine kappa. So kappa becomes imaginary number. So in this region, I cannot define Q. So outer edge can become imaginary kappa. So so this is the star formation rate density here and volume density here. So I can see linear unstable region with Q lower than 1 corresponding to the Clump positions. Okay. But the important thing is that the interclump region, so the disk region out here, is not lower than 1. So Q is high, about 2 or 3. The color is green or yellow, something like that. And I can see a nonlinear instability regime around the clump. So what I want to say is that clump region, inside the clump and around the clump may be unstable, but this region is stable in two-dimensional analysis. Okay, next one. This is okay. Okay, next galaxy, next sample, and this galaxy has high gas fraction, but result is the same. We can see many galaxies here, and the clump is unstable region with purple color can be seen around the clumps only. So the interclump region has Q higher than 1, green or yellow. Okay. Okay, now, so the interclump region, this region has high Q. So what I want to know that, so what Q values does the clump formation start with? So this is now, I'm showing volume density here and the Q map here. So look at here, this is a plot clump region. Okay, next one. And next one. Next one. Now clump formed here. But initially, this region has high Q. The color is green. It's about 3. Q equal about 3. So the clump formation happens, start with high Q, and after the clump formation, the Q value becomes lower than 1. Okay, like this. Okay, next, another example. So look at here. There's nothing. There are many few diffuse gas cloud can be seen here, and Q is of course higher than 3, and this region contract, and Q became a little bit lower, and the clump formed here. Q became lower than 1, and the clump forms, and Q become an unstable region. Okay. Okay, this is showing the statistics of the Q value at the proto-clump region. So I performed a clump detection scheme invented by New Mandelker, and I applied this method to all snapshots. So I can trace back the clump orbit to the formation position and the formation time. So and I measure Q at the formation position of the clumps. So this is what I call proto-clumps. Okay, this is the histogram of Q value on the proto-clump positions, and these three indicates different galaxies. Okay, so now, so this line is Q equal 1. So this region is linear instability regime, and this is blue is Q equal about 2. This region may be unstable in tubular instability, but significant fraction of clumps has Q higher than 2. So these clumps are supposed to be tubular stable, but actually these are proto clumps, so they become clump. Okay. So the conclusion is that significant fraction of clumps, not all, but significant of clumps start forming with high Q, higher than about 2. Okay, so yeah, that is my main result. So what I want to discuss with you that, so what is the true formation mechanism of the clumps? So I listed up some possibilities again, as many as possible. Okay. So the non-perturbative scenarios can be possible, for example, gas cooling, or small scale formation. Tubular instability may start from very small 100 parsec scales or something like that, and grows non-linear by accretion or mergers between clumps, something like that. Anyway, and on the other hand, non-axisymmetric perturbation is also possible. So tubular instability is axisymmetric perturbation. Non-axisymmetric works differently. Okay, and the perturbative scenarios also possible, and minor mergers. Merger bombardment disturb the disk, and the disturbance may form clumps. And the cold stream flowing in the disk. The cold stream join in the disk with maybe a slow velocity or counter rotation. These gas will be unstable. And pre-existing clumps cause compressive turbulence by the pre-existing clumps. This is related to the talk by Neil. Okay, so my summary is here. My main conclusion is that Q is generally high in the disk region, and clump formation start with high Q. So I can say that clump formation is not the standard tubular instability. Okay, that's it. Thank you very much.
Thanks. Have you tried different smoothing scales? Because it seems to me that you are focused on the instability on the scales for 1 kiloparsec.
Yes.
But the resolution is much better, so clumps may form much smaller scales. And then aggregate or some kind of different instability.
Yes. So the reason why I applied this smoothing scale is that to focus on the mass scale of, this mass. So I applied a smaller smoothing. I can look at smaller mass scale. So, and when I applied half KPC smoothing, of course I can see small instability structures. I can see small clumps. So, but interclump region is still higher than 1. Sorry, interclump region has still Q values higher than 1, higher than 2.
I was just going to ask a simple and perhaps less sensible question, which is, the kind of stability analysis that was originally done by Tumorin has been done by Ravikov and other people. Usually what you do is you come up with some dispersion relation and then you analyze the stability of modes of different sizes. And here you're applying the Q parameter to a very local scale that is in some sense insulated or doesn't know about the larger system. And I'm just wondering whether Q, since you have a kappa, which you've defined here, which is different than other kappas, if it's precise enough to within a factor of 2 to know whether local stability is a strict condition or not.
Yes, first of all, yes, of course, tumor analysis is local analysis, so, and the global instability may happen even if Q is higher than 1. Yes, and
The dispersion relation corresponds to different weight numbers of different sizes.
yes, yeah, yes.
Thanks very much.